Okay, moving forward, a little bit more about land surface models. As we said, they need to represent the vegetation and other land use like forest, agriculture, urban landscape, deserts, and so on in some way, either fixed in time, seasonally varying, and those are typically picked up from satellites like MODIS, moderate resolution infrared spectrometer, or some such thing, which gives land use types at some resolution in time and space, and typically people are either prescribing it year to year, season to season changes during an integration, or taking a climatology of it and prescribing it for longer integrations. But of course you have to be very careful, because if your integration goes from let's say pre-industrial time to the present and to the future, then you have to find a way to represent them in the past as well and into the future. So lots of details there. One of the most important processes for land surface models is soil moisture and evapotranspiration. Evapotranspiration is basically evaporation mediated by vegetation, so water going through the vegetation and then exchanged with the atmosphere when the stomata is open and so on. And the details of soil capacity, soil properties, groundwater exchange, runoff, and the entire hydrology is all incredibly complicated, and it's all very important for the energy exchange between the land and the atmosphere. So obviously they affect energy balance, precipitation, local microclimate, and so on and so forth, and there are lots of parameterizations required there as well. So you have important processes like runoff, which is the water that's collecting and being flowing in hydrological structures, natural and artificial, and there is the soil capacity, root depths, and all kinds of details can be needed. Depending on the model, they can be simplified but also can be very detailed in some models. So there is the canopy interception of the precipitation, which could be snow or rain, for example, and there is the canopy cover, which affects albedo, surface roughness if the model is doing that kind of detail, and leaf area index is something that is also computed from satellites like MODIS, which affects the interception of energy, precipitation, solar energy, outgoing long wave, and so on and so forth. And evapotranspiration creates aerodynamic resistance and so on, and there is canopy stomatal resistance as well for the process of hydrology of water being picked up through the roots, bringing up here and exchanging with the atmosphere. For example, if the carbon dioxide concentration is increasing in the atmosphere, then some models want to worry about stomatal conductance. Remember, stomata is open to capture CO2 for photosynthesis, and they want to optimize the time of opening, because they don't want to lose this water, precious water they have brought up from the roots to the atmosphere. So then the stomatal conductance has to change when the CO2 increases, because now the stomata doesn't have to remain open that long, and this is found to have some impact on the hydrology, because the trees are not losing as much water anymore because of closing the stomata faster in a higher CO2 level, but also the warming of the atmosphere and increase in its water holding capacity can increase the vapor pressure deficit, which is basically ability of the atmosphere to hold moisture and the actual moisture that's present. So in that case, again, opening of the stomata can lead to higher loss of water vapor because of this vapor pressure deficit and so on. So there are some processes that are known but cannot be represented explicitly, so they have to be represented as parameterizations, and some processes are not completely known, but we know they are important, and the details, molecular level details, are not represented, but they are parameterized as well. So of course there are also details like how the surface roughness varies, how the surface albedo varies, how that affects local warming, soil moisture loss, soil moisture persistence, and so on and so forth. So incredible amount of details go into these models, especially in terms of seasonality of the agriculture, irrigation, impact of irrigation on water balance, evapotranspiration, cooling, and so on and so forth. Okay, so I will leave it there. You can read much more. There is an enormous amount of literature on each of these components. Obviously, we are not going to get into those here because we are mostly focused on just introduction to climate modeling for either processes or for climate change. Okay, sea ice is another incredibly important component of the climate system, especially because it affects the albedo and the heat exchange between the ocean and the atmosphere. In addition to that, it's also a strong feedback in terms of the ice albedo feedback. So there is again wind, and there might be some rustling sound in the recording. Apologies for that. But processes of ice formation and its impacts on the ocean and the atmosphere and the energy budget are all obviously very important, especially because now polar amplification is such a prominent feature of the climate system response to anthropogenic forcing as well. So schematic of some of the processes in a sea ice model: net surface heat fluxes at bottom and surface, FB and FS. So you have sea ice floating and has a generally much smoother surface because the wind blows the smooths out the surface, whereas the bottom tends to be very jagged, and I will say why in a minute. They are exchanged with the ocean and the atmosphere above respectively. In this example, there is a snow layer of thickness HS and temperature TS at the surface. So you have sea ice thickness and then you have snow on top of it. And two ice layers with temperatures T1 and T2. So there is a near surface layer that's interacting with the atmosphere more closely than the layer below. Beyond a certain thickness, that layer is not as closely interacting with the atmosphere as the upper part of the sea ice. So that's a detail as well. And an overall ice thickness of HI. The ocean also exchanges heat directly with the atmosphere through the so-called leads. Wherever there is a gap in the sea ice, that's called a lead, and there the heat exchange between the atmosphere and ocean can be orders of magnitude larger than here, because sea ice is a good insulator. Wherever there is sufficiently thick sea ice, the heat loss is greatly reduced from the ocean. And if the ocean is in liquid form, obviously it's above 0 degrees centigrade. Of course, with salinity it can be below 0 and still not freeze, but the atmosphere at these latitudes is typically very cold. So the heat loss here can be very high from the warm ocean to the cold atmosphere, whereas it can be heavily blocked here over the sea ice. Those are very important details as well that the model has to capture. Ice movement depends on a balance of several forces, the largest of which are indicated by arrows here. So you have water drag. So the currents below could be related to wind forcing or large-scale circulation or slopes under the water and so on. So there are internal ice forces that are creating ice movement as well, and wind drag. So there are all these things that are determining where the ice is going, how fast it's moving, and that also affects its thermodynamics and how quickly it can grow, for example. Okay, the largest of which are indicated by arrows here. During freezing, rejection of salty brine from the ice tends to increase ocean salinity, which means when water begins to freeze because you are pulling enough heat out of it, then the molecules of water get organized systematically with the hydrogen bonds and so on, that they reject the salts, and that is brine rejection. So sea ice or any kind of frozen water does not have too many salts in it, especially compared to the ocean water. So what does that mean? That means during melt, as increased surface heating causes surface bonding and warming waters cause lateral and basal melt, fresh water is returned to the ocean, right? But when the sea ice is forming, that brine rejection increases the density of the water below, so the water tends to sink and then new water has to come in. So some kind of a circulation gets set up, which means new heat is being brought. So typically if you look at ocean, look at the ocean sea ice distribution, it tends to be largely what is called pancake ice. Unless the ocean is closed like the Arctic or it's a lake, for example, the sea ice and the lake ice, they don't get very thick because of this property of brine rejection, heavy water formation, and the recirculation that gets set up and the new heat that gets brought in. So typically land ice or glaciers can grow kilometers thick, but the sea ice cannot grow very thick. Arctic is special because it's semi-enclosed and it has very fresh waters due to all the runoff and so on. Fresh water is easier to freeze, of course, so there the sea ice can get very thick. But if you go to open ocean like the Southern Ocean, you don't get sea ice as thick as in the Arctic necessarily. There you get glaciers flowing onto the ocean and you get shelf ice and not so much thick sea ice. So you have, of course, sensible and long wave radiation balances happening here, determining the surface reflection of solar radiation and high albedo and so on. So you have surface flux here and heat energy exchange and heat exchange here, and there are also freshwater input from the lateral melt and so on that we talked about, and the basal melt. So all these processes have to be accounted for by a sea ice model. Sea ice modeling is now quite advanced. It started way back in the 70s, for example. Many ocean models run with fully coupled sea ice models. The land ice models are fairly new. In fact, previous IPCC projections didn't even have land ice. Land ice has whole different other set of issues, because land ice is basically snow that falls, doesn't melt through the winter, more snow falls next year and it gets compressed and forms glacier, which is not frozen water, it's compressed snow. So that actually has properties of rheology, which means it's like molasses. It can flow, especially when it forms on the mountain. It can flow down the mountain onto the ocean, which makes for other complicated issues like warm waters melting the shelf ice from below or breaking it off because of the tides heaving the shelf ice and so on. So Antarctica, for example, is having a lot of these shelf dynamics which make the glacier slide, melt faster, get unstable, and so on and so forth. So those processes are much more complicated, but now there are more and more glacier or ice sheet models as well. Okay, so maybe I should leave this here, but let me just add the climate drift as well, which we discussed before. So here is observed climate over time. Let's say some climatology remains fairly constant here. The model may be initialized from the observed conditions, in which case once it is coupled and integrated forward, it has a so-called climate drift. So even when the model reaches its equilibrium after long integration with prescribed radiation forcing at the top, volcanic forcing, solar activity, land use types, and so on and so forth, it reaches an equilibrium that has got a slight drift compared to the observation. But if you start from random conditions and not from observed condition, the model tends to reach the same equilibrium after a long time integration of several centuries. So average gives climate state here, and you can see that the other simulation is basically coming to the same mean state, but it may still have variability that's different because the differences in the initial condition are carried forward for a very long time. So often, as we saw before, the spin-ups, so-called spin-ups, where the models are integrated, ocean, atmosphere, land model is integrated with the, let's say, pre-industrial level of CO2 for many decades, sometimes centuries, depending on the computation time you have available. And then the drift is not complete yet, or the drift has reached its constant, and then you integrate forward into the 20th century and 21st century and so on. So the projections can account for the model drift, as we saw before, in giving the projections for the future, or even in describing the model simulation for the 20th century. So this is important always, that the models will never completely match the observations everywhere. They may do better in some places than in others, and some models may do better than other models, as we will see in a minute. So this is just a schematic example of model integrations during spin-up to a simulated climate state. So you can think of this as the pre-industrial revolution simulation to start the 20th century and 21st century simulations. The value of temperature, the temperature shown could be either a global or a regional average. The value of temperature for the observed climate is indicated with this dotted line here. Two runs are shown, one from an arbitrary initial state conditions and one from the observed initial conditions. The climate model runs have much natural climate variability, and so smooth curves are added that show the main features of the spin-up. Times in centuries, as would be appropriate for a full climate model, just in terms of how long it takes to reach equilibrium. In fact, asynchronous integrations are done because the ocean can take much longer than the atmosphere to equilibrate, and longer than the coupled model. So the ocean can be integrated separately to reach a statistical equilibrium or some steady state with its drift, and then couple and then integrate the coupled model forward. So those are kind of details. Similar curves but with a faster time scale would apply if only the upper ocean were included in the model, or if a regional climate model were used. So that many times you may compromise and use only the upper ocean to simplify the integration, to speed up the integration, and so on. So all those are strategies which depend on what the goal of the simulation is. If the goal is future projections, then obviously you cannot ignore the deeper ocean at all. Okay, so let's leave this here for now.